So now let's talk about some common contexts for conditional probability. Well, in conditional probability, one of the I still hear this all the time whenever I hear like drug commercials and things like that. Or even, when you go to the doctor's office and you have a test, they might tell you some of this information. Often in medical testing, it's not necessarily that you have a disease just because a test says that you have the disease, right? There might be a false alarm error, right? They might say, oh, you have the disease, but actually you don't, right? Or a pregnancy test is another example where it might say that you're pregnant, but it's actually just a false alarm, right? On the flip side, you could have a miss where you actually have the disease, but the test turns out to be negative, right? So there are all these issues with medical testing. And because of that, conditional probability is really important. When you have some sort of medical screening, you want to have positive predictive value. This really means that given that the test is positive, right? Because, when you're like the patient, all you know is the test result, right? Given that the test is positive, right? What is the actual probability that you have the disease, right? What is the probability of disease given that you already got a positive result, right? Is it 100%? Is it 90%? Is it only 10%? I mean, what is that? And as this positive predictive value, we might also call it PPV, as this goes up, the better your test is. That's one measure of how good your test is. You want this to be high. If you get a positive result, you definitely, you don't want to have the disease, but you definitely want to know, okay, this really means you have the disease. But that alone is not enough. It's not enough. It's not enough just to have high PPV. You also need what's called high sensitivity. And this is the opposite conditional probability. This is the probability, given that you have the disease, right? Given the disease, and this we don't know. We don't really know if you have the disease. What is the probability that the test is positive, right? Given this condition, what's the probability that the test is positive? Because imagine, let's say people have this disease, right? But the test doesn't always show that you have this disease. That's a very different space than the probability of disease given the test result being positive. So we need to know both of these things in order to figure out whether a medical test is any good or not. Okay, so that's one area where conditional probability turns out to be very important. And understanding that these two things don't equal each other is really, really important. Because oftentimes doctors might just give you one of these or one of these, right? Usually it's this one, right? Doctors or companies might tell you this one, but they might not tell you this one. But you really need to know both in order for you to make an informed decision. The other place where conditional probability is very commonly used is in statistical testing. In statistical testing, we often have some data, and we want to know, is this model likely, right? So here we might want to know, what is the probability of me getting this data, getting this empirical sample, right? Sample data, given some theoretical model population, right? Some theoretical population. So given a model, right? So we have some sort of model, right? Like we think, oh, people are guessing randomly, or this is a fair dice, or whatever our model of the universe is. Oh, there's no differences between these two groups of people. Whatever our model is, we want to know, what is the probability that I'll get this particular set of data? And it's good to know this. But we actually also would like to know the flip side in order to make an informed decision. So the probability of a particular model given my sample data. And in fact, we would really, really, really like to know this one because we do already have the sample data, right? So we want to know how likely is our model now that we already have our sample data. But this is actually really impossible to calculate because in order to calculate this, you would have to have some sort of model in the first place. So, so yeah, usually we use this, but really in an ideal world, we would really want to know this as well. But this is often unknowable in statistics. There are some cases where they've done what's called model fitting, looked at how likely is this model given data, but that's much beyond introductory level statistics. All right, now let's move on to some examples. So in example 1, we have some sort of medical test, right? So this pharmaceutical rep shows these drug testing results to suggest that this drug is very accurate. I guess you take a drug in order to take this test. I don't know. He says, this test detects this very rare disease 90% of the time. Is there any reason to think this drug isn't that great? Well, when he says it detects this disease 90% of the time, is he saying 9 out of the 10,000 people who took the test? No. He's really talking about 9 out of the 10 people. So when he says 90%, he's really saying the probability of a positive test, given that they have the disease, positive test given disease is 90%, right? So this is what we call sensitivity. This test has good sensitivity. When you definitely have the disease, it's highly likely that you'll have a positive result. But is there any reason to think that this drug might not be that great? Well, we might want to calculate the positive predictive value, right? So this would be the probability of disease given a positive result, right? And so in this case, we're looking at this world. The test is positive, right? Given this world. And that would be 9 out of 59. So 9 out of 59. And that's 15%. So 15% of the time, when you get a positive result, you have the disease. That means 85% of the time, when you get a positive result, you don't have the disease, right? So imagine, this patient comes in, they're really worried they have some disease, they take this drug test, look at the result. Oh, it's positive. What should they think? Should they think they definitely have the disease? No. There's an 85% chance that they don't have the disease, that it's just a false positive. And so there is a reason to think that this drug isn't that great. They have pretty poor positive predictive value. This is pretty low, right? And, just to put it into sort of regular terms that a patient can understand, this means that even if you have a positive test, you don't know whether you have the disease. There's an 85% chance that you don't, right? So that's not a great test, right? So maybe that's why this drug isn't that great. Okay, so example 2. Suppose Mike draws marbles at random without replacement from a bag containing 3 red and 2 blue marbles. Oh my God, this really sounds like probability, right? Whenever you see red marbles and blue marbles. Remember, he's drawing them without replacing them. So whenever he draws a marble, that marble is no longer in that universe, right? So now it's conditional probability. Given that you don't have this marble, what's the next world like? So find the probability that the second draw is red, given that the first draw was red, right? So red, red sequence, right? Well, it might help if we talk about the first draw. Oh, let me draw this in black so that I could talk about red marbles and blue marbles. first draw, and then maybe we'll also put in second draw. And I'm going to draw a tree diagram, and I think I'm going to need a third draw, so might as well put that in right now. Third draw. Okay, so let's talk about the first draw being red. Oh wait, first draw being red or first draw being blue. So what is the probability that my first draw is red? I don't know why I put P, R, right? Well, it has 3 red and 2 blue marbles, so the probability of first draw being red is 3 out of 5. And so my probability, the flip side of the first draw being blue, is 2 out of 5. And so when you add this together, you get 1. Because either this or this has to happen. One of these has to happen. All right. Now, by the time we get to the second draw, here we have 5 marbles in the bag. Here we only have 4 marbles in the bag. Here we're only going to have 3 marbles in the bag. So I'm just going to write that to help me out. What is the probability of drawing another red marble? Well, by the time I get here, there's only 4 marbles left. And we've already taken one of these guys out. So there's only 2 red marbles left. So that would be probability of another red one, given red, is 2/4 or 1/2, right? But the probability of getting blue is this. Probability of blue given that I just drew a red marble. Well, here, I still have my 2 blue marbles left, right? Because I didn't draw a blue one out of 4. So that's 2 out of 4. And once again, these 2 add up to 100, or 1. Okay, so now we could look at, okay, what is the probability that my second draw is red, given that my first draw is red? Well, here, I figured out that probability. That probability is 1/2, right? So given my universe, this is my new universe where it's where the first draw was red, this is my probability of drawing another red one. Well, what is the probability that my second draw is red, given that my first draw was blue? Okay, so now we have to do this bottom part. Well, what is this probability that my second draw is red? Okay, so here, I know that I only have 4 marbles left, but one of the ones that were taken out was a blue marble. So I still have my 3 red marbles left in there. So my probability of red, given that I just drew a blue one, is 3 out of 4. Right? And on the flip side, the probability of blue, given that I just drew a blue one, is 1/4, because now I only have 1 blue marble left, right, out of 4 marbles. All right, so here I could say my probability of red given blue is 3/4. All right, so finally we come to see what is my probability that the third draw is blue, given that my first and second draw is red. So here I could just follow this branch, right? So of my tree. So red and red. First and second one is red and red. So now, what is my probability? I don't really care about this red one. I just really care about this blue one. What is the probability that I draw blue? Well, now I only have 3 marbles left, and I haven't drawn any blue ones. So there's 2 out of 3 marbles that are blue. So my probability of drawing blue given 2 previous red ones equals 2/3. And my probability of drawing red, I've already taken out 2 red ones, will be 1/3, and so that'll add up. And so this right here, I'll write 2/3. Now we have a pretty high chance of drawing blue, even though we started off with fear blue, but because we've taken out all the red ones.